So this integral here is called the Sophomore's dream. It's called like this because the result of this integral is ridiculous, honestly, but you will see why in just a few minutes. Now, I hate this negative x in the exponent of x. I mean, duh, I really do. So I would like to rewrite this integrand as e to the ln of x to the negative x, because now the laws governing logarithms will enable me to drag that negative x in front of the natural log, and now, well, I'm integrating just an exponential. Let me now, kind of out of the blue, honestly, evoke the power series for e to the power of x. If I plug negative x ln of x into that power series, I will just get my integrand. So let me replace my integrand with that power series for e to the negative x ln of x. The awesome thing is that I can actually change the order of summation here, because my integrand is convergent on my interval. I can, without a single problem, integrate first and then sum instead of summing first and then integrating. So I will now get this sum, this infinite sum of those integrals. I would like to now make myself a u-sub here. I would like to set the negative ln of x equal to a u that will make the dx equal to negative e to the negative u du. As to the bounds of integration, whenever x goes to 0, u is gonna be the negative natural log of 0, so negative of the negative infinity, that will be the positive infinity. Whenever x goes to 1, u is gonna be the ln of 1, that is 0. Now plug all of that stuff into the integral, it will look something like this. The problem is that we're integrating between infinity and 0, but I don't really like it. But I can use the negative sign in front of the du to flip those bounds of integration so they look, well, normally. Now we can also take this e to the negative u, which was, well, the part of my du, and just kind of suck it into the e to the negative u times n. Now, I still don't really like this integral. I mean, it's still kind of messy, so let me maybe do something about that. I would like to make another u-sub here. Maybe I will call it a t-sub, for example. So I would like to set n plus 1 times u equal to the t. This will make n plus 1 times du equal to the dt, and the bounds, well, then they don't really change. So the resulting integral is going to be this integral, in the same bounds, but of e to the negative t all over the n factorial times t to the n over n plus 1 to the n, and then times dt by n plus 1. The nice thing is that those n's, all those expressions with, only n's inside of them, they are just constants with respect to x. I could just take them out of the integral altogether. So let me do it, and also combine that 1 over n plus 1 to the n and 1 over n plus 1, so they become 1 over n plus 1 to the n plus 1 power. Notice one more thing. This integral from 0 to infinity of this e to the negative t times t to the n dt, this is the gamma function, which actually simplifies to be just n factorial. And I love it because this factorial here is going to cancel out with the n factorial in the denominator I've got in front of the integral. And so what I'm going to be left with is just this simple looking infinite sum of 1 over n plus 1 to the n plus first power. But it looks kind of messy, so let me just kind of shift the indices here. I would like to start summing not from n equal to 0, but from n equal to 1. And then I can just rewrite this summand as 1 over n to the power of n. And so I get this, whoa, awesome result that the integral from 0 to 1 of x to the negative x dx, which is a continuous sum, is going to be equal to this sum over all of the integers n, apart from 0, of 1 over n to the n. So a continuous sum is going to be equal to the discrete sum, and it's blowing my mind off, honestly. So that would be the Sophomore's dream. Anyway, I hope you guys enjoyed it, and see you in the next one.